is Mate Puljiz from University of Zagreb, Croatia. And today I'll be talking about market microstructure and order book dynamics in crypto. And first of all, thanks to the organizer for the opportunity to speak here, and for all of you to cutting your lunch break early and coming here to hear this talk. I should also mention that this work is joint work with Stjepan Begušić and with Zvonko Kostanjčar. We are part of this laboratory for financial and risk analytics that was recently founded, and a couple of other guys in machine learning techniques are also part of it, so you're very welcome to check out our website. It's written up there, and see what other things we're doing, and get in touch if some of the stuff is interesting. Okay, so to start, what is the problem that I would like to have a look at today is the modeling of the cryptocurrency market, or in general, modeling any sort of double auction market. So I assume most of you are fairly familiar with this notion. So basically what you have is a limit order book in which people who want to buy a thing and people who want to sell a thing come and write their orders. So they write down how much stuff they want to buy or sell and at which prices. And this is described in usual terms as limit orders. They put basically in this limit order book, the orders that get executed immediately are market orders, and then of course they can pull their orders back, and that's something that is called the cancellation order. And of course they can either buy and put their orders on the bid side of the order book or on the ask side if they're selling. And the goal is to have some model for the dynamics of such a thing. And there was this paper in 2010 by Kohn, Stoikov, and Talreja, which created a nice mathematical model for such a thing. And it was based on the queuing theory. So what is a queuing theory? It's a basically probabilistic model which is describing the queues. So you have people coming into the queue, and you have the server who's serving the customers, and the people are incoming at a certain rate, and the server is executing is serving the customers at serving rate. And just based on these two parameters, if you assume the incoming customers are a Poisson point process, and the same for the outgoing rate, you can basically compute some quantities that are of interest, such as the average length of the queue, average time spent in the queue, and so on. And what these guys did in this paper was sort of putting this queuing theory on steroids. So they created the order book model in a way that they put a bunch of queues together, and then they try to model the incoming and outgoing rates to these queues. So let's have a look at this picture. So this is actually from the Bitstamp exchange, bitcoins to US dollars. It's a snapshot at a certain time when the price was around 10K. So this is what you usually see. You have the buyers, which are depicted in blue, and the height of this column at a certain price level describes how many orders you have outstanding at that price level. And as you can see, buyers we describe with negative values, and sellers, orange ones, are described with positive values. And this is a nice way, basically, to describe the state of the complete order book at any point in time. And each of these price levels is a separate queue, basically. So you have orders incoming to that queue and outgoing, and then you need to provide the parameters for all of those queues, but that will ultimately give you the complete dynamics of your order book model. Okay. So more formally, you have a fixed price grid. So in our case, we took the tick size to be $10. And at each price level, you have the random variable xi at t, which describes the amount of orders at that price level. If the number is positive, that means you have a buyer at that level, and if it's negative, it's a buyer, and if it's positive, it's a seller. And then you can also define the standard quantity, such as ask price to be the smallest price level at which you have the positive random variable, and similarly to be bid price to be the highest price level at which you have negative variable x. Another schematic picture of this would be something like that. So you have these orders that want to buy and the orange ones that want to sell, and then you represented it basically just as an integer vector. So -1 corresponds that one outstanding buy order, then -4 is to that outstanding, to those 4 outstanding buy orders at that level, and so on. So you represent the whole state of the book just with this integer vector, and then you just need to provide the dynamics on such a state space, and the dynamics is provided by a Markov process, which, as we said earlier, is just a bunch of queues for which you need to specify their incoming and outgoing intensities. There is another assumption, so you basically assume that at any point either an order can come in or go out. So you assume that you have some chunks and those chunks are indivisible. So either an order comes in or goes away, and so the increments are going to be just of size 1. So at each time t, if you have a state of your book xt, then at some next state where the limit book changed, is going to be changed to xt plus ei or minus ei, where ei is just a vector of zeros with 1 at position I. And now we need to describe those arrival, cancellation, and market order arrival and outgoing intensities, and these are described with arrival intensities and cancellation and market order intensities, which are denoted by lambda, theta, and mu. And these parameters are going to be the parameters of those Poisson processes from the queue in theory. Okay. So this is in formulas how these intensities look like. So it's actually quite intuitive. So I'll try to go just to explain on the first part. So how do you transition from rate x from state x to state x prime, and where x prime is just x plus ei? Well, what's going to happen basically, if we go back to this picture here, so if your price level at which your order is arriving is to the right of the best ask, then that means that basically just you have an extra order arriving, extra sell order at that price level. And that's going to be dictated by the lambda I, which is the arrival intensity of limit orders at the distance I from the best opposite, in this case, from the best bid. So that would be the third line saying lambda of I minus PB. So you basically measure the distance from the best bid, and then you have your parameter lambda, which tells you what's the incoming intensity at that price level. If you look at the first line, it is basically saying what happens if your price level I is to the left of the best bid. Well, in that case, because you're increasing your counter by 1 at that position, that will correspond to deleting an order from the bid side of your queue. And that can only mean that either that order was actually canceled or that order was executed against another market order. So, and actually it can be executed against another market order only if it's precisely at the PB level, which denotes the best bid. So in that case, you have this parameter mu, which is the intensity of market orders, plus the intensity that comes from the cancellations, which you need also to multiply by the current number of the orders you have at that price level, which is basically because if you have 10 orders at a certain price level, then it's more likely that some of them will go away or will be canceled than if you have just 2 of them. So you need to account for that, and that's why you're multiplying by these random variables x's. And then it's completely symmetric situation in case you're decreasing your counter. And all the other rates are assumed to be 0. And the nice thing is that now this completely determines the dynamics of this probabilistic system. So you have your numbers lambda I, theta I, and mu, and that gives you all the information you need to simulate such a thing. And then you can test it against your real double auction market and see how it behaves. It also gives you, so because it's now a fixed probabilistic model, you can try to compute probabilities of the movement of the price, which you can then use for prediction and see how that behaves and how that corresponds to your real market. One thing that one always has to have in mind when building a model is what one assumes. So we assume that the orders come and go one by one, which is not an unrealistic assumption, because you can always shorten time sufficient. You can take a short enough time interval, in which that's basically satisfied. But more importantly, it's assumed that the times between the orders is independent and exponentially distributed, which comes from the assumption of the Poisson point process, and also that the queues themselves are, in a way, behaving independently. And we also here assume that, so we're going to take some period of time and we're going to estimate these parameters, and then we're going to check them against the data. So in here, we assume that these parameters are fixed for the whole observed period. Yes? No, so actually I said that they are, these queues are independent, but as you've seen, they are defined relative to the current best bid and best ask, and that in a way makes them dependent, but there's no additional modeling of the dependence between the queues, other than that is accounted with the parameters. Okay, so it is a nice, cool model, but of course it has its problems. Yes?
You don't make any assumptions about the shape of the queues, right? Because usually when you look at the exchange, you'll find that there are many times that there are more sellers and more buyers the further away you go from the price point. So basically have a triangle that sort of faces or meets up at the point of the price.
Yes, so you're not assuming that, but you're... It will emerge when you're estimating the parameters, yes. Okay, yeah, so now we're coming to that part. The exchange we used was Bitstamps Bitcoin to US dollars exchange. The reason we used that was because they have this open API which pushes to you basically all of the order data. So you get a stream of everything that all the market participants have published, basically in the limit order book. And then from that, we locally reconstruct the full order book and the trading dynamics. The period we're looking at was fairly randomly chosen. So we took 300 hours worth of data, and as I said, we used a tick size of 10, so we discretize. Of course, you have the tick of the exchange itself, but because you want to be able to estimate these parameters, then you need a big enough tick size, so you actually, within the time period, you have enough orders coming in into your, basically bin into your queue, so that you can give, you can get reasonable estimates. And how do you estimate these parameters? Well, it's fairly natural. So what's going to be the incoming intensity is going to be the number of limit orders in the observed period divided by the time period t, and also divided by 2, because here we were looking at the symmetrized version of the model. So we collect all the limit orders on the market and on the bid and the sell ask side, and then we need to divide by 2 to split it evenly between those two. In order to estimate thetas, which are related to cancellation orders, it's the same number of cancellation orders divided by 2t, but also you need to divide, and this is what your question was, so you need to divide by the average number of orders that are I ticks away from the opposite best. So in a way, you're not assuming it in the model, but you're estimating your parameters with that in mind. So in a way, it comes into play. Okay. This is actually how these quantities look like on average. So this is the steady state of the order book for this observed period of time. And what we see is this similar shape of these, of the order book as in the conventional market, so as in the article I mentioned before. So they look at all these estimates, and then basically the shapes are similar, and what you see is basically that the largest number of orders is about 5 ticks away from the opposite best, which in our case means $50, and the average spread in this observed period of time was about 2 to 3 ticks, so about $20 to $30. So that's sort of comparable to what they get. Okay, and again, I plotted bid and ask separately, but what we use is actually the average of the two. I haven't said yet how we estimate the market intensity, and it's written here. So again, it's number of market orders divided by 2t, but what you need to do now as well is to account for the fact that in general, and you can see this in your data, that market orders are smaller than the limit orders they eat on the other side. And in this other paper where these guys created the model, what they have is that this, basically the amount of market order that is needed to eat one limit order is 1 to 2, or closer even to 1. And here what we see is that it's actually more like 4 to 3 market orders that are needed to eat one limit. So this is, of course, on average, in terms of their average sizes. Okay, so you need to account for that just by multiplying your intensities of market orders. And then what it turns out that we get actually better results if you do what you think it's natural to do, which is to estimate market buy and market sell separately, in a sense that the multiplier for my market buy is going to be average market buy order divided by average limit ask order, and similarly, well, the opposite for the market ask. So that's the difference between these two multipliers. Okay. Once you have those parameters, you also need, I haven't told you, well, I told you what they are, but this is now the plot of those graphs, and this again behaves or looks like in the conventional exchanges, like the results they've got in the other paper. So what you see is that the largest orders on average are about 10 to 11 ticks away from the current best opposite, which of course makes sense, right? So if you want to sell larger amounts if you want to sell larger amounts of bitcoins, then you want to be a bit away from the current best prices, because you're trying to make the least market impact you can. Okay. This is now plotted. So in this picture, we have plotted all the intensities for this observed period. Note that market bid and ask well, it's just one number. So it's the blue and orange one. And note that in this observed period, the market intensity was, market buy intensity was stronger than market sell intensity. And so we again see the familiar shapes that are observed in the conventional exchanges for the lambda and theta parameters. One thing that's not clear in this picture, but which you can actually get just by multiplying this theta with the average number of orders at that distance from the opposite best tick. So remember that incoming order intensity was just lambda, but outgoing order intensity was theta times the number of orders outstanding at the price level. So in order to get the comparable numbers, you would want to multiply your theta by the average number of orders at that price level, which was the picture we had here. And if you multiply basically this graph with the red graph here, you get pretty much the green graph. What does this tell you? Well, this tells you basically that the incoming and outgoing orders match, which in a way is what it should be, but what you can also, so what we also find is that this is in a way a byproduct of the fact that there is a lot of this undercutting that we heard of in the previous talk. So you have basically a lot of orders being immediately put and then canceled and put and canceled, and this, now one could say artificially or not artificially, it's just the situation the way it is, you get these intensities in a way inflated more than you would expect. So especially at the smallest price level, well, at the price level that are closest to the best bid and best ask. Okay, so how do you validate your models? So one thing that the Kant and the co-authors propose is that you compute the movement of the mid price. What is mid price? All of you know it's just the average of the bid and ask. And, well, all of you know what the spread is. And then it turns out that in this model, because it's completely determined by its parameters, you can compute the probability that the mid price goes up, given that your spread is one tick wide. So we have a situation like in this picture here. So you have bid, and then $10 away you have best ask or less. And then if you collect all the orders you have at the best bid, that's your number minus B there. So remember that bid buy orders are denoted by negative numbers, and on the best ask you have A orders. And then the probability that your mid price goes up, if you think about it, is just the probability that the Q, the orange Q at the PA level goes down to 0 before the Q at the PB does. So basically that's the only thing that can happen. So now if you have orders that come at to the right of the best ask or to the left of the best bid, they will either not affect the best bid or best ask, or they will eat up best bid or best ask, or they will increase the best bid or best ask. So you can sort of, that's the beauty of this model. You can just, basically, if the spread is 1 tick, then you can just consider those two Qs, and based on their incoming and outgoing intensities, you get an analytical formula for this probability, which you can then compute, and that gives you something to check against your real data. And this is, in a summary, what we get. So this matrix is a matrix of, given that you have a spread of 1 tick wide, and given that you have 1 to 5 orders on the best ask and 1 to 5 orders on best bid, what is the probability that the model gives on the left, and what is what you observe in your data, because you can of course see whether your mid price went up or down in the next time step. And you can see that these are fairly similar, and the numbers also match quite well. You also see the thing you would expect. So if you have plenty of orders on ask side, but very little on the bid side, then it's more likely that the bid will go down first, and then it's more likely that the price will actually go down. So that's why you see the light areas in the top right corner of the matrix, and the opposite is, of course, for the top left part of this matrix. You can compute how much these matrices differ, and this is also, the result we get is comparable to what these guys get for conventional exchanges. So in a way you could say this model is well fitting the data, but you could also argue that there are some problems with it. So one thing to notice is that for market intensities, I sort of made the situation non-symmetric, but for limit orders and cancellation orders, I've symmetrized the situation, and we did this because this improves the model accuracy. And one reason for this could be is that just because you have more of data, then you get better estimations of the parameter in this way. But it's also, it could be something else which we overlooked. So that's definitely something that that we will try to improve. Also, as I said before, it seems that the incoming and outgoing intensities are inflated, artificially or not, but they seem to be. So there's a lot of this undercutting that we've heard of before. So what is the further work? It was mentioned also. So what about the dependencies between the queues? It would be interesting to see if there is a nice way to add the dependencies to the model, other than just based on these these incoming and outgoing rates that sort of take account of that with us explicitly demanding any dependencies. It's also interesting to try to infer the true supply and demand, so sort of to mitigate the effects of the traders that are constantly undercutting the best offers. And of course, ultimately what would one want is to devise trading strategies that would use such a model to make informed decision on how to trade. So actually I wanted to show you just another small video of the, so it's just a small period of time that you can, once you have this model, then you can take the real data and create an animation. So yeah, if you can. Yeah, so that's the. So this is what the dynamics looks like. So you have the timestamp up there. And what you can see is that around the best prices, again, reiterating what we said and what we've heard before, there is a lot of this activity, the orders coming and going, disappearing and being created again. Note that here we have tick size of 10, so it could be, so it's basically just flipping between the two states, the limit order book. And the more away from the core activity, you have these orders that are more stable in a way. So in a way, what we would like to do is, in a way, try to abstract away or to take away the influence of these noise traders and somehow try to infer the long-term behavior of the market based on these more stable traders. But that's something we haven't haven't yet resolved. So that's something that we're certainly going to be looking at in the next period. Okay, and then that's basically all what I wanted to talk about today, and I want to thank you all for your attention, and if there are any questions.
Yeah, I'm gonna pick you, and then lots of questions. We try to get them all. Yeah.
Just a question. How do you validate the assumption that you really follow process? You have data.
Yes, so it's actually it's because in a way the model concentrates on the, well, at least that's what we were looking at this point, was at those the orders that are so at the best bid and best ask, and those orders are arriving at such a quick rate that it's well, you just get plenty of them. So it's, and because of the problems of the socket that's streaming the data, you cannot basically rely on the fact that perhaps. So what happens often is that you get plenty of orders bunched up together at the same time, but they weren't actually executed at the same time. So it's just sort of the problem. So yeah, we haven't, the answer is we haven't checked for that because the data is so frequent that we weren't able to rely on the timestamps that we get, basically. So that's the short answer, right? So we thought that, yeah, it wouldn't be meaningful. Yeah.
Yeah.
So have you investigated whether the parameters are stable over time?
Sorry, that was the 35. Again.
The parameters you estimate, they were from January, February this year, right?
Yeah, so this was a
Are they stable?
No, so yeah, they also change, and that's also something that we would very much like to look into more. So how to model the change of these parameters. So they do change. Yeah, so that's also a problem.
So
Yeah.
if you're going to use it in sort of auto-trading model,
Yeah.
then you need to re-estimate them every day or whatever.
Exactly, yeah. So we were trying to do that sort of thing, of course, just locally and trying to see if we can do anything. The problem is, of course, you're talking here about the mid-price move, which is not the long-term price move, which is what you would like to, of course, be able to predict. And then, of course, if you take into account the trading cost, yeah, so we weren't able to devise yet the trading model that would earn, basically, that would beat the market. Okay.
You had a question?
Kind of related question. So if you condition like the estimation based on aggregate price and then up or down, would it make a difference for parameters? And also if you do this like employee window estimation,
So,
like, would it be these parameters is persistent or like they completely like change your idea?
yes, so they do change quite a lot, and then again, depending on which window you're taking. And then for the conditioning of the current state of the book, that's what you're asking. Well, yes, you can do that, and we try to do some sort of, well, something like that. But then you're in the, well, if you condition too much, then you get too little data. That's what can happen. So you have just plenty of situation you need to consider, and then you have just too little data to estimate parameters meaningfully. So yes, we haven't been able to make that work yet.
Andrew, you had a question?
So in your setting, it's for the order book determining the bid price, right?
Yes, yes.
Causality story. That would be that actually I'm going to submit my order by looking at the bid price, and then it will determine
Yes, so we haven't looked into that, so into our impact on the order book yet, but that's definitely something that makes sense, yeah, so that's something that...
maybe not in your setting because algorithm trading is not really an important thing, but when you have an algo, it becomes in that way, right?
Yeah. Yes, that's something we need to look into, yeah.
Any more questions? Yes.
So the tick size of $10 seems pretty arbitrary.
Well, it of course is going to change the intensities because they, in a way, depend on which bin size you take. But we tried it with different bin sizes, and the qualitatively you see the same picture. So in terms of the statistics of the average shape of the order book and all those parameters. So qualitatively, you get the same picture.
Any remaining questions? If not, I have one final question. So the predictions you showed, were these sort of out of sample?
No, so they were inside. So that's the problem, to make them work out of sample, because you need a good way to estimate parameters in future. So that's. I mean, in a way, it's nice because you have a parametric model of your order book, right? So that's something that's also something that we're sort of looking into trying to do, to use these intensities, feed them into machine learning algorithms, and try to see if they can spit out something meaningful. But yeah, that's work in progress.
I mean, something that you could try would be to see if you just were to train a classifier on the prediction, to what extent you improve your prediction if you do not just take the Markov state, but like latest earlier states as well, right? Into your
so,
prediction.
Yeah, but these intensities, they have a meaningful explanation. So it would be nice if you could, just based on them, create the model that works, right?